welcome everybody. So yesterday on my video I sort of introduced organic chemistry to you, gave you an idea of some of the properties of the compounds, and then also talked about some of the applications that are important. But don't get me wrong, there's many types of or different applications that can be applied for organic chemistry, and you'll see that throughout when we start talking about different compounds and why they're important. But today what I wanted to really focus on was the first type of organic compounds that you're responsible for knowing, and those are the hydrocarbons. And when we talk about hydrocarbons, it's important to know how we can express them. And there are really three ways that we use, or three types of formulas that we use to express hydrocarbons. And a hydrocarbon, if you haven't guessed it, it contains only carbon and hydrogen. So now, what would be a typical hydrocarbon? Well, take for example something like C3, or I should say, let's actually do C4, C4H10. Now this molecular formula, it tells you how many carbons and hydrogens there are. We could actually reduce this even further. We could make it an empirical formula. So we could have something like C2H5, and this would be the empirical. But we generally don't use the empirical formula because it doesn't give us the true formula, how many carbons and hydrogens they are. Now you might look at this and be like, well, this gives me quite a bit of information. It tells me how many atoms are in the compound. What more could I want? If I have the number of particles in there, there's nothing really else that I could really want. And so there is more though, because what we're really interested in is the structure. And the structural formula, what it will tell us is it'll show us the carbons connected to one another. And it'll show us the carbons connected to the hydrogens. And so here is now my structural formula. Now, if you recorded how long that took me to draw that, it was at least 10 seconds compared to the C4H10, which was like 1 second. So the structural formula takes more time to draw. It's more intensive. But also, it gives me a lot more information, which is really helpful. Now, the thing is that that's sort of annoying to draw out a whole big structure. So there's kind of this middle ground, the condensed structural formula. And that kind of gives us the same amount of information that the structural formula does, but it sort of condenses it down into something smaller. And so if I were to do that, I would have like CH3. So I would show the C connected to the three H's. Didn't show up, that's weird. There it is. And then I have CH2, which is my next carbon, another CH2, my third carbon, and my my CH3, my last carbon. So this shows me all of my carbons still connected in the correct order, and it shows me the number of each atom. So it's giving me a structure, but it's not showing me all of the bonds. Now you'll see both of these used throughout the chapter, so you have to be aware of them. Now look, why is the structural formula important? Why isn't it just enough to say C4H10? Well, C4H10, what if I were to give you something like this? What if I were to give you C4H10? So now I've drawn a different molecule here. They have different names. We're going to name them in a little bit, but just to give you a little preview here, this is called butane on the left, and this is called methylpropane. So we have butane, we have methylpropane. They're different compounds. And if I were to draw their condensed structural formula for methylpropane, it would be something like this. It would be CH3, CH, parentheses, CH3, and then CH3 again. And when I draw parentheses like this, it's showing me the side group that's hanging down there. So I have my CH3, that's a side chain, and I highlighted that also in the condensed structural formula. All right, so let's talk about the three types of hydrocarbons called homologous series. The first type is an alkane. An alkane is a saturated hydrocarbon, so they call this saturated, much like saturated fats that you see here. And This saturated alkane or hydrocarbon has a general formula of CnH2n plus 2. What that tells me is N is the number of carbons, and I can find the number of hydrogens. Take, for example, my butane, C4. Now I would plug that in. H, 2 times 4 plus 2, and that gave me my C4H10. This is given to you on a reference table. I'll show you that in a second. Now the thing about alkenes is that they all have single bonds connecting the different carbons, and so they contain all single bonds between carbons. So when I drew my butane before, I had 1, 2, 3, 4. I drew all single bonds. For carbon to have an octet, I need a total of 4 bonds, so now I'll fill in the rest with hydrogens. Now just to save some time, I won't write each hydrogen in, and this is actually acceptable to do this. Now what about an alkene? Well, an alkene is considered unsaturated. It has the general formula CnH2n. Now if we were to look at that and say, all right, well, let's do a but for this one, so let's do C4. Now it becomes H2 times 4, which would be C4H8. Now if we draw this, we'll see that we have a different number of hydrogens. We can't have all single bonds. There has to be some sort of multiple bond that's taking up some of those electrons and not allowing enough hydrogens to bond to make 10. So we would do our 4 carbons, but now we would have a double bond. Now the next carbon already has 3 bonds, the second carbon already has 3 bonds, so it only needs 1 more hydrogen. The third carbon would need 2 hydrogens to form an octet, and the last carbon would need 3 hydrogens to form an octet, and now I have my unsaturated hydrocarbon. I would call this butene. And to be exact, I would actually call this 1-butene. Now you might be wondering, oh, well, where is that number coming from? Like, where is that 1-butene coming from? It comes from the fact that, again, I can draw a different structure for this, just like I did with the butane and the methylpropane. I can draw a different structure for this, and it would look like this. It would be C connected to C like this, but now I could put the double bond here. And so on the left, I need 3 hydrogens. This carbon would get 1 to make an octet. This carbon would get 1, and this carbon on the end would get 3. And this would actually be called 2-butene. Now I know this may seem sort of weird, like where is he coming up with these numbers? And honestly, we're going to spend a lot of time, probably in the next video, really going through how to name them and why you number the carbons. If you sort of see this, you might be saying to yourself, oh, wait, I number the carbons because I need to tell where the double bond is. But we'll go through in more detail in the next video when to number and when not to number. Lastly, we have alkynes. So alkynes have a triple bond. If we did 4, we would have a triple bond. The general formula for these are CnH2n minus 2. These are also unsaturated. And so now when I go through this, I need to fill out the right number of hydrogens. Well, let's figure it out. We have 4 carbons. 2 times 4 is 8, minus 2 is 6. The carbon on the end only needs 1 hydrogen. The carbon in the middle has 4 bonds. It doesn't need any hydrogens. The third carbon needs 2 hydrogens, and the last carbon needs 3 hydrogens. And there we have it. So now we have what they call butane. But guess what? We need to tell where the triple bond is. This is actually 1-butane. And just like we had a 2-butene, ENE ending, we could also have a 2-butane. And again, we'll go over when to number and when not. The carbon on the end should get 3. The second carbon doesn't need any hydrogens. The third carbon doesn't need any hydrogens. The last carbon needs 3. It's still a total of 6 hydrogens. Now, there are other types of hydrocarbons that I just want to touch on before I end, and one is called a cyclic hydrocarbon. Carbon's very special because it can make these chains, long chain molecules, but it can also form rings. And so a common example is pentane. That becomes a cycle, and this would actually be called cyclopentane. And so then we would have our hydrogens coming off of this. We could have a pentene too, where we have a double bond. And so that would look something like this. And now this carbon would only have 1 hydrogen. This would have 1 hydrogen. 2, 2, 2, and 2. And so this would be cyclopentene. And the last ones I want to tell you about are the aromatics. Now those aromatics, they actually are ring structures that have double bonds alternating with single bonds like this. And they would have 1 hydrogen coming off. These actually have a general formula like the other types of hydrocarbons. These are called the benzene series, or arenes. And they have a general formula CnH2n-6. Some interesting ones of these, if we take off one of the H's and put a methyl group, I'm going to draw it shorthand just to save time, double bond, single bond, double bond like this. And if we were to put in a methyl group, this becomes called toluene. That's the common name for it. And we could also have, where we have this benzene group, and we add an OH group to it, and this actually would be called phenol. So this is some basic hydrocarbon stuff going on here. You can see that different carbons can form single bonds if you're saturated. Saturated meaning the maximum number of hydrogens. You could have alkenes and alkynes, double and triple bonds, and that would be what would be known as unsaturated. You could have cyclic hydrocarbons where they form these ring structures, and you can have aromatics that are also ring structures but have those double and single bonds alternating. So this is just a general overview of the different hydrocarbons. Next time we'll actually talk about identifying the types using the tables and naming the compounds. All right, thanks so much for watching.